Hello everyone. Today, we will study the drying devices of printing presses. Function and requirements of drying devices. Proper drying is critical for ensuring print and coating quality. The drying devices ensures rapid solidification of ink and coating liquids to prevent smudging and blocking of printed sheets. Requirements for drying devices. First, must not alter the color of ink, coating, or substrate, nor cause dimensional changes in the substrate. Second, the drying device should be small in size, convenient and flexible to use, and harmless to people and the environment. Third, parameters of the drying device can be steplessly adjusted according to changes in printing format size, printing ink layer, varnish layer, and printing speed. It can automatically disconnect when the machine stops and be isolated during machine adjustment to prevent excessive temperature. Types of drying devices. After glazing coating, drying is essential. Therefore, drying devices for sheet-fed lithographic press glazing coating include air-blowing drying, infrared dryers, ultraviolet UV dryers, and emerging electron beam EB dryers, etc. Dryers generally adopt a plug-in installation structure. First, air-blowing dryers. Air-blowing dryers use a blower to press air toward nozzles, creating forced convective heat exchange on printed materials. As needed, hot or cold air is used to dry ink or varnish on the substrate, though the drying speed for ink or varnish is relatively slow. Second, infrared dryers. Infrared drying is a method using radiative heat transfer for drying. Its principle is as follows: the electromagnetic waves generated by an infrared radiator propagate linearly at the speed of light to the material being dried. When the emission frequency of the infrared rays matches the natural frequency of molecular motion in the material, that is, the emission wavelength of the infrared rays matches the absorption wavelength of the material, it causes intense vibration of the molecules in the material. This intense friction inside the material generates heat. To achieve drying, infrared dryers can be constructed in tubular or blade shapes. Infrared radiation quartz bulbs serve as radiators, with electrically heated glass shields, ceramic, or metal sheets, etc., as reflectors, to direct infrared rays onto the coated printed materials. Third, ultraviolet UV curing units. UV curing is a method using irradiation curing. The principle is that free radical photoinitiators in UV coatings or inks, typically acrylate polymer systems, are irradiated by ultraviolet light of a specific wavelength, triggering decomposition to produce free radicals. This initiates polymerization, cross-linking, and grafting reactions, instantly transforming the coating or ink from a liquid to a solid state. UV curing units typically use tubular air-filled quartz lamps, filled with argon and mercury vapor as radiators. Their radiation is focused onto the substrate via elliptical or parabolic reflection devices. Due to the high energy consumption but low effective energy utilization of UV mercury lamps, only about 20% of input energy generates ultraviolet light, which causes a series of problems. In recent years, more environmentally friendly and efficient LED UV curing devices have gradually become mainstream. LED UV light energy is highly concentrated in a specific UV spectral band effective for curing. UV inks are classified by absorption wavelength, primarily absorbing wavelengths of 365 nanometers, 380 nanometers, 390 nanometers, 395 nanometers, 400 nanometers, etc. Because LED UV curing systems with wavelengths above 390 nanometers are less expensive, Currently, 390 to 400 nanometers band LED curing systems dominate the market. and LED UV inks are mainly suitable for this wavelength range. Advantages of LED UV curing. 1. Low energy consumption and high effective luminous efficiency, reducing energy consumption by 70% to 80%. 2. No ozone generation during curing. LED UV curing system light sources do not produce short-wave UV, so no ozone is generated during curing. 3. Low heat generation, high photoelectric conversion efficiency of LED UV light sources, making them less likely to deform heat-sensitive materials during curing. 4. Long service life of up to 20,000 hours, more than 10 times that of traditional mercury lamps. And the service life is unaffected by the number of switch cycles. 4th, electron beam EB curing units. Electron beam curing is a new type of irradiation curing method. Electron beam EB for short. The curing mechanism of EB inks is basically similar to that of UV inks, both belonging to irradiation curing. The difference is that EB inks do not require photoinitiators and use electron beams as the radiation source. Electrons emitted from a set of linear cathode plates are accelerated through a vertical uniform electric field to obtain high-energy electron beams under the accelerator irradiation chamber. The high-energy electron beams generated by the accelerator, with energies typically ranging from tens to hundreds of keV, are tens of thousands of times higher than chemical bond energies. Therefore, when coatings or inks are irradiated, they can be directly ionized and excited. The main components of EB ink binders are acrylate prepolymers and reactive monomers participating in the reaction. Acrylic resins are highly unsaturated. When irradiated by high-energy electron beams, molecules transition from the ground state to the excited state, and unsaturated double bonds are broken, generating free radicals or ions. Then, through free radical initiation, free radicals react with C equals C double bonds to form growing chains, causing cross-linking polymerization between oligomers and monomer molecules to generate network polymers, rapidly curing the ink into a film. In the entire process, electron radiation acts like a special initiator in the chain initiation stage. Once polymerization begins, subsequent reaction steps are independent of radiation and proceed according to ordinary polymerization reaction kinetics. Due to the high energy of the irradiated electrons, the above reactions are often accompanied by side reactions such as molecular degradation and molecular ion rearrangement. Therefore, EB-cured coatings exhibit greater branching and higher cross-linking density. Unique advantages of EB curing compared to UV curing technology. 1. Fast curing speed and high quality. EB inks typically cure in just 1/200th of a second under electron beam irradiation. The strong penetrating power of electron beams ensures thorough curing of the ink, due to the formation of high molecular three-dimensional network polymers through ink cross-linking reactions. The pigment concentration is high, resulting in beautiful print appearance, strong gloss, and three-dimensional effects. The ink film surface also has strong chemical and abrasion resistance. 2. Environmentally friendly and safe. The solid content of EB inks after curing is nearly 100%. Generally, they contain no VOCs, volatile organic compounds, causing no pollution to the environment or packaging, with little or no odor, and minimal harm to workers. Since no photoinitiators are used, there are no photoinitiator residues in EB-cured inks, making them safer. 3. Low energy consumption. EB curing consumes 5% of the energy of UV curing and 1% of traditional thermal curing. 4. Less heat generation. EB curing is a cold processing method, especially suitable for heat-sensitive substrates like films. avoiding excessive heat that could cause deformation, leading to reduced printing quality and failures. 5. Reduced cleaning and convenient storage. E-inks do not need to be isolated from air during storage. And e-inks in the ink fountain do not form skin or harden. Reducing waste. Main disadvantages: high cost of EB curing equipment and large one-time investment. Requires a strictly controlled inert gas environment for curing, etc. 5th, combined drying. Using only one of the above drying devices to dry printed materials in modern lithographic presses is far from sufficient. Combining these methods is a common practice and the future development direction. This concludes today's lesson.